So in the previous class, we have completed question number 4 of May-June 2022, paper 4-2. Now we are going to start with question number 5. Okay. What they are saying? Complete table 5.1 to predict the substance liberated at each electrode during the electrolysis of indicated electrolyte with inert electrodes. Okay. So we have a molten lead bromide. In this case, we have only lead ion and a bromide ion. So at anode, bromide ion would attract it and turns into a bromine, and at cathode, lead ion would attract it and turns into a lead metal. So here the answer would be bromine and lead. Is this understandable to everyone? Yes.
Yes, sir.
Okay. Now we are using aqueous concentrated sodium chloride. So here we have sodium ion and a hydrogen ion are the positive ions, chloride ion and the hydroxide ions are the negative ions. So out of these two positive ions, hydrogen ion would undergo, because of lowering reactivity, forms hydrogen gas, and because of a higher concentration, chloride ion turns into a chlorine gas. So here I would write chlorine at anode and hydrogen at cathode. Is this clear? Now, in this case, we have a copper nitrate where there are copper 2 positive ions and nitrate negative ions, and as it is aqueous, so there must be a hydrogen ions and the hydroxide ions. Whenever there is a case that there are nitrate ions and the sulfate ions, in that case, hydroxide ion always oxidizes at anode forming oxygen gas, and copper is low in reactivity series than hydrogen, so it would reduces at cathode forming copper metal. So the substance liberated at anode would be oxygen gas, and the substance liberated at cathode would be a copper metal. Is this understandable? If anyone have any doubt, kindly ask. Yes, is this clear?
Yes, sir.
Okay. Now, an electrolytic cell is set up to determine the value of Avogadro's constant L. The electrolyte is dilute sulfuric acid and both electrodes are copper. Okay, the current of 0.65 ampere is passed through acid for 30 minutes time. The anode decreases by the mass of 0.350. So that is the change in mass. So state the relationship between Faraday's constant F and the Avogadro's constant L. So if you recall this, it is that Faraday's constant is equals to Avogadro's constant times charge of 1 mole of electron, charge of 1 electron only. Okay. Now what they are saying that use the experimental information in B and data from the table on page 23. Calculate the value for Avogadro's constant L. So if you look in page 23, there would be a value for the Faraday's constant, that is F, that is 96500 coulombs or 9.65 exponent minus 4 coulombs. So it's page number 23. So here you have a value. So we have to that we can use this value. Let's check whether we are able to use this value or not. No, 1 minute. If you recall, I have taught you whenever we use this expression, we don't use the constant, but we calculate that constant. So the value that we are going to use from the table is the charge of one electron, which is also on page number 23, and here it is. So not this one, but this one. We are going to use this value from the table on page number 23. That is, the charge of one electron is 1.6 exponent minus 19 coulomb. Okay. So here we go. Okay. So the charge of an electron is 1.60 exponent minus 19 coulomb. Okay. Now, if we look at the data, what we know that we can relate the charge and the mass. And as they are copper electrodes, so it would be Cu2 positive ions, the half equation or the reaction cathode would be this. Okay. So according to the question, we have used 0.6 ampere current for 30 minutes time. So which must be times 60 to turn into a second. And for that much coulomb charge, the mass deposited is 0.350 gram. So if you look at the equation, here we have a 2 moles of electrons, and these 2 moles of electrons are producing 1 mole of copper. So I would keep here 2 moles of electron and would take the mass of 1 mole of copper because it's a mass in grams. So I would take a mass of 1 mole of copper. And if you look in the periodic table, it is 63.5. So for 2 moles of electron, when the charge of 2 moles of electron is passed, 63.5 gram of copper is produced. So from here, when I find the value of 1 mole of electron, the charge of 1 mole of electron, that is 0.60 times 30 times 60 times 63.5 divided by 0.350 times 2. So can anybody solve and tell me the answer?
Sir, 97971.
Sorry?
97971.
97971, right? So
Yes.
these are the coulombs that are carried by 1 mole of electron. So that is actually considered to be a Faraday. So to find the Avogadro's constant L, it is equals to F over E, where F is 97971 divided by E, which is the charge of 1 mole, 1 electron, that is 1.6 exponents minus 19. And here you would get the Avogadro's constant. So can anybody tell me the answer?
The 6.123 exponent 23.
6.123. So for the 3 significant figures, we can skip 3. So 6.12 exponent 23. So that is the answer for this question. Is this clear to everyone?
सर हमने वो क्यों नहीं इस्तेमाल किया फैराडेज कांस्टेंट एक्चुअली में?
Yes, that's what I discussed earlier as well. Whenever we have to justify the Avogadro's constant from the electrolysis method, that L is equals to 6.02 exponent 23. So we don't use the exact constant. Instead, we calculate it that during the experiment that is performed, what would be the value for 1 mole of electrons, what would be the charge, and it never exactly the same. It would be always differ from 96500, and we use this charge, not that one. Okay.
Okay, sir.
If anybody else have any doubt, kindly ask.
So why have you written like 2 electrons instead of 2 Faraday?
Yeah, it's I just use it to write, to represent the symbol. You can just write 2F as well or 2X as well. It doesn't matter.
Like it's the same thing, right?
Yeah, that is the same thing. I can write over here 2F. I can write over here 2X. And here I have mentioned that it is, see, if you see over here, I have mentioned that it is, sorry, 1 mole of electrons charge, and I represented it with F. So you can write just 2F over here as well. Okay.
Okay.
Okay. Now, this is question number 6. The reagent and conditions required for the nitration of benzene, benzoic acid, and phenol are shown in the table. Okay. To nitrate a benzene, okay, we need these conditions. For benzoic acid, we need these conditions, and for phenol, we just need dilute nitric acid at 20 degrees Celsius. Okay. So if you look at these conditions, we can easily, relate their reactivity, and I can say that this one is the most reactive, right? This one is the least reactive, and it is of moderate reactivity. Is this understandable to everyone? Okay, now what they are saying, concentrated nitric acid reacts with concentrated sulfuric acid to generate a electrophile NO2 positive. Okay. Figure 6, complete figure 6.1 to show mechanism for the reaction between benzene and the nitronium-ion NO2 positive is called nitronium-ion. Include all relevant curly arrows, okay, and charges. Okay, so here in the first case, you can show the arrow arises from the pi system of a benzene towards the nitrogen, pointing towards the nitrogen, and as a result, we will make the intermediate having a benzene ring and a partial circle inside. That NO2 is bonded to a carbon, and you have to show the hydrogen that is also bonded to a same carbon. Then show a curly arrow from the bond of carbon hydrogen bond to the inside the benzene ring, and as a result, the pi ring is stabilized.
रिंग के अंदर पॉजिटिव चार्ज नहीं होगा?
Yeah, sorry, I forgot. I completely forgot. So there is a positive charge along with the semicircle. Thank you. And the H positive is released. Is this understandable? This is the mechanism for 3 marks only. Okay. Then what they are asking, write an equation to show how H2SO4 is regenerated. So when H2SO4 and HNO3 reacts, what would happen? The reaction would happen like this, that H2SO4 and HNO3 when reacts, H2SO4 releases a hydrogen forming hydrogen sulfate ion. The water is formed because from HNO3, OH negative is released, which is joined by the H positive that is released by the sulfuric acid, and we got NO2 positive over here. So during this reaction, sulfuric acid turns into HSO4 negative. Now the regeneration equation would be that HSO4 negative again joins with H positive, forming H2SO4. So that would be the equation that how sulfuric acid is regenerated. Is this clear to everyone?
Sir, can we
Here-
make H3PO plus with instead of H2?
Yes, that's what I'm doing. That it's an acidic medium, so two sulfuric acid would releases two hydrogen ions, so it would becomes actually H3O positive due to the acidic conditions. Okay, is this clear to everyone?
Yes, sir.
Now, draw the major products from the mononitration of benzoic acid and of phenol. Okay, so here we have to show the mononitration when a single nitro group is being substituted in benzoic acid. This is benzoic acid. Then what would be the major product? And when we have a phenol, and on phenol, when we do the nitration and when nitro group is going to attach, then what would be the major product? So if you recall, this benzoic acid is an electron withdrawing group, so it substitute the next group either at third position or a fifth position. So we place a NO2 group over here, and in this case, the OH is an electron donating group. So when the electron donating group is attached to a benzene ring, then the next substitution would occur at carbon number second, fourth, and sixth. So either you can make NO2 over here, or you can make NO2 over here. Both are considered as correct. Is this clear? Yes.
Yes, sir.
Okay. Now compare the relative age of nitration of benzene, benzoic acid, and phenol. Explain your reasoning. Include reference to the structures of the three compounds in your answer. Okay, so see, that's what we have already figured it out. The easiest one is the phenol because its nitration is occurring at 20 degrees Celsius. If you look over here, and the hardest one to nitrate is a benzoic acid because its nitration is occurring at 100 degrees Celsius. And the moderate one is a benzene itself. So here we have a trend. Now we have to explain this. First, tell me, is this clear to everyone?
Yes, sir.
Okay. So in phenol, the p orbital overlaps with pi system as a result. It attracts the NO2 positive more readily. See that overlapping of the p orbital is the p orbital which have a lone pair of electron. So when that lone electron actually induces, okay, let me draw over here. This is phenol. So in phenol, when oxygen overlaps, it induces its electron towards the benzene ring. So due to this, there is more electron charge density. Hence, it can attract that positive electrophile more readily. Is this understandable? Yes. If anyone have any doubt, kindly ask.
सर कहते हैं can we say that OH due to OH being attached on the ring कहते हैं O increases the negative charge on 246.
No, we can say that O induces its electron in the benzene ring, or the pi system of a benzene ring.
Positive inductive effect.
Then, when we talk about benzoic acid, so in benzoic acid, that COOH group with withdraw electrons at its withdrawing in nature. So what would happen over here? See, here you have a benzoic acid. So it withdraws electron from the benzene. As a result, here in the pi system, there would be a lower electron charge density because the electrons are withdrawn towards the carboxylic group. So I can write, hence it attracts the NO2 positive less likely. Is this understandable to everyone?
Yes, sir.
So further we can comment that in phenol, the electron density in pi system increases, and in benzoic acid, the electron density of pi system decreases. Is this understandable to everyone?
Yes, sir.
Okay. Now, if you look at this B part, the azo compound Congo red is used as an acid base indicator and can be made by the route shown in figure 6.2. Okay. So here, that is the Congo red. In step 3 of the synthesis, compound Y reacts with compound Z. Okay, these are the two compounds. And compound Z is made from compound X. Assume SO3 Na2 positive does not react. So you have to keep this in mind that SO3 negative Na positive does not react. Okay. So if you see over here, if you look at the whole scheme, these bonds are indicating me that here the coupling reaction took place and a dye is formed. And if you see over here at Y, you are observing the sulfur and sodium which is over there, which clearly indicating me that basically Y is this compound. So I would make a Y over here with two benzene rings, and out of these two benzene rings, one benzene ring have NH2 group, and directly opposite to that NH2 group there is a CO3 and A positive group. So we have figured it out what is Y. Is this clear? Now it means the leftover part is this, which actually initially which was a benzene diazonium salt. So basically this would be your Z. But in Z, this is actually the residue from the Z, but actual Z would be two benzene rings bonded to each other, and where there are nitrogen double bond, there would be a nitrogen triple bond in a benzene diazonium salt having a positive charge. So this would be the Z. So this the actual product helps me to identify what are Y and Z. Is this understandable to everyone?
Yes, sir.
It is Z, a benzene diazonium salt, then this benzene diazonium salt, if you recall, see here we have a 2 nitrogen and here we have 4 nitrogen. It is always formed from diamine. Oh, sorry, phenylamine. So the X would be
Diphenylamine.
yeah, the same structure, but the only difference is that where there is a nitrogen triple bond, where we have NH2 groups on both the sides. So that is the X. So that's how we attempt the question. Is this clear?
Yes, sir.
Yes, if anyone have any doubt or any confusion, do ask. Okay, so that's what they are asking. Suggest the structures of X, Y, and Z and draw them in the boxes in figure 6.2. We have completed this. Now what they are asking, give the reagents and conditions for step 1 and step 2. Okay, if you see in step 1, these NO2 groups are turning into NH2. And if you recall, this is a
रिडक्शन
reduction.
होगी ना सर स्टेप 1 में
Yes, reduction where
इन
we
और
use
concentrated HCl के साथ
very good Z, tin and concentrated HCl, and we have to heat the mixture. So for step 1, I would write tin and concentrated HCl along with heating or reflux. Now in step 2, the amine is turning into benzene diazonium amine. And if you recall this reaction, in this reaction, we use NaNO2 and HCl at a temperature below or equal to 10 degrees Celsius. So that's what we are going to write over here, that NaNO2 and HCl, and the temperature would be less than or equal to 10 degrees Celsius. This reaction occur at cooler temperature. So our question number 6 is completed. Yes, if anyone have any doubt, kindly ask. Now, question number 7. State the use of TMS, that is tetramethylsilane, and D2O in NMR spectroscopy. So, if you recall, TMS, it is used as a reference and if you recall D2O, that D2O is used to
It, it is used to
identify.
identify NH and OH bond.
Very good. OH or NH. These protons which I underlined, these hydrogens will be identified. Okay. Now what they are asking, the 3 isomeric ketones with a molecular formula C5H10O are pentane 2-on. If I made a pentane 2-on, it would be this. Then pentane 3-on, it would be this. And then if I write 3-methyl butanone, so 4 carbons. So this would be 3-methyl butanone. Now, what they are saying, complete table 7.1 to show the number of peaks observed in proton NMR spectrum and in the carbon 13 NMR spectrum of each of the compound. Okay, let's start with pentanone. It's CH3, C double bond O, CH2, CH2, CH3. Now, these hydrogen and these hydrogen are going to be different with each other in terms of their chemical environment, because one is bonded to the CH2 group and the other one is bonded to a carbonyl. This hydrogen is different from the others because on both of the sides there are methyl group, and these hydrogens are also different because on one side there is a carbonyl and the other side there is a methyl. So 1, 2, 3, 4. So we are going to get 4 signals in proton NMR. Now, if you look at the carbon, so if you look at the carbon, this carbon differs from this one. This carbon is also different. This carbon is also different. And this carbon is also different. So we are getting 5 different carbons with respect to their chemical environment. So we are going to get 5 signals over here. Okay. Now, let's have a look at pentane 3-on. So it would be CH3, CH2, C double bond O, CH2, CH3. So if you see, these 2 protons are similar, so they are going to show you same signal. These 2 protons are similar, so they are going to show you same signal. And there is no other protons. So in proton NMR, we are going to get only 2 signals. But if we talk about the carbon 13 NMR, so this carbon is completely different, so it have a different signal. These 2 are relative, are similar carbons, so these 2 are going to show you same signal, and these 2 carbons are exactly similar, so these 2 carbons are going to show you same signal. So it means there are 3 different kinds of carbon over here, so we are getting 3 signals over here for carbon 13 NMR. Now we are left with 3-methyl butanone. So if you draw its structure, here a CH3, then C CH, then again a CH3, then C double bond O, and then CH3. Okay, so if you see these hydrogens are similar, so they are going to show you one signal. This hydrogen is different, so it is going to show the second signal, and these hydrogens are different than the rest of one, so it is going to show you the third signal. So here I'm going to get 3 signals in the proton NMR. Now, just a minute, please. Now have a look at a carbon for carbon 13 NMR. These 2 carbons are going to show you same signal. Then this carbon is going to show you the signal different than these 2. Then this carbon have a completely different signal than the rest of one. And in the same way, this carbon is going to show you the different signal. So in terms of proton NMR, carbon 13 NMR, we are observing that there are 4 different kinds of carbon, or 4 different types of carbon. So we are going to get 4 signals in carbon 13 NMR. Yes, is this clear to everyone?
Sir,
Yes.
so when you count the hydrogens on the neighboring carbon, so like till which carbon do we count that?
Sorry, I didn't understand.
I mean, when we are counting the number of hydrogens bonded to the neighboring carbon, so do we only count the carbons that are directly attached, or we change?
Wait. The the hydrogens that are attached to a neighboring carbon will give us a splitting order of that signal. We are not talking about the splitting order. For example, if I talk about these 3 hydrogens, they are going to show a one signal, but as there are 2 hydrogens are neighbor to this one, so it means this signal is going to split into a triplet like this.
Right.
Okay, in the same way, these 3 hydrogens are going to show me a signal, but on the neighboring carbon there is no hydrogen, so it would be a singlet. So the neighboring carbon would show me that how the signal would be going to split, but the number of carbons on a specific carbon, and when we look at into its neighbor, would tell me that it is these hydrogens are actually different than this one or not these. So that would help us to identify how many number of signals we can obtain in the proton NMR.
Right.
If there is still confusion, do ask.
It's clear now.
Okay. Now, state all ketones with a molecular formula C5H10O that have a doublet in their NMR. For a doublet can arise only when the neighboring carbon or the adjacent carbon have one hydrogen, right? Yes. Then we are going to observe a doublet. So if you see, in this case, there is not a single carbon where there is a CH. So this would not be the answer. In this case, if you observe, there is again not a single carbon where there is a one hydrogen. But if you look over here, this is one hydrogen. So it means the signal of these 2 is going to split into a doublet, because on neighbor of this there is one hydrogen only. So I would write over here that there is 3-methyl butanone, its proton NMR spectrum would show a doublet, a signal as a doublet. And the rest of the two, the pentane 3-on and the pentane 2-on, would not going to show me a doublet in their spectrum because there is no CH group over there in those two compounds. Is this understandable?
सर वो हाइड्रोजन डिवाइड हो जाएगा.
Why? Remember, we discussed that there is a n+1 rule for the splitting pattern where n is the number of hydrogens on neighboring carbon. Let
Sir,
me
but
show
it
you.
has 2 hydrogens.
Sorry. Can you repeat again what you are asking, please?
Sir, the carbon has 2 hydrogens.
Yeah. You are talking about which carbon? First tell me. See, let me tell you. For example, this carbon have a 2 hydrogen, right?
Yes, sir.
So if we are observing the low resolution NMR, so I'm going to get a 1 signal only. But if I observe this signal in a high resolution NMR, so the signal of these 2 hydrogen is going to split into a quadrate that is 1:3:1, because on adjacent carbon there are 3 hydrogens, so the value of n for this would be 3, so n+1 becomes 4. So that's why I'm getting quadrate over here for these 2 hydrogens.
Yes, sir.
Now is this understandable or still confusion?
No, sir, I understand that.
So here what they are asking, that a doublet in the spectrum. So if there is a doublet in the spectrum, which means that n+1 would be equal to 2. So if I find the value of n, it would be 2 minus 1, which gives me 1. So it means that 1 hydrogen on neighbor carbon. Right?
Yes, sir.
So this is the only one structure where there is a 1 hydrogen on a carbon. But if you look at these 2 structures, in these 2 structures, there is not a single carbon which have only 1 hydrogen.
Okay, sir, understood.
So it means when we observe the spectrum of these 2 compounds, I am not going to observe a doublet, a signal as a doublet. But when I observe the spectrum of this compound, I am going to observe a signal as a doublet, because here we have a 1 hydrogen, which is actually neighbor to these 2. Is it clear to everyone now?
Yes, sir.
Yes, if anyone else have any confusion to ask. Okay, now a singlet in their proton NMR, which means again, if there is a singlet, then it means n+1 is equals to 1. So if I would find n, it gives me 0. So it means no hydrogen on adjacent carbon, right?
सर वो पेंटेन 2 ऑन में होगा ना जहाँ पे ये
Sir, pentane 2 on.
And is there any other compound beside pentane 2-on?
3-methyl
3-methyl butanone.
Yeah, 3-methyl butanone, because if you see at these 3 hydrogens in their neighbor carbon, there is no hydrogen, so this would be a singlet. And here these three hydrogens as their neighbor carbon have a no proton, so here I am going to get a singlet. But in this compound, we are not going to observe a singlet. For example, if I look at these hydrogen, so this neighbor doesn't have a singlet, but this neighbor doesn't have a hydrogen, but this neighbor do have a 3 hydrogens. So this is going to split into a quadrate. So for the next part, where they have asked you a singlet, so the answer would be these 2. So I will write pentane 2-on and 3-methyl butanone. Is this understandable? Yes, is this clear?
Yes, sir.
Okay. Now the C part. Cortisone, having this molecular formula, is a naturally occurring chemical that contains chiral carbon atoms. Reduce the number of chiral carbon atoms in a one molecule of cortisone. Okay, do it quickly and tell me how many number of chiral carbon atoms you guys are getting. Yes, do it quickly.
Sir, 4 है.
Okay, Rida. Yes, anyone else have any suggestions?
Sir, 6 है. 6.
Okay.
Yes, sir. 6.
Okay. So here is a one chiral carbon. There is a second one, third one, fourth one, fifth one, and the sixth one. So yeah, 6 chiral carbons. Okay, next part. Cortisone is reacted with an excess of NaBH4. If you recall, NaBH4 is a reducing agent which reduces aldehyde and ketone only. State the molecular formula of the organic compound form. So it's easy. If you see, there is a ketone, so what would happen? It becomes a single bond, one hydrogen added over here and one hydrogen added over here. This is a ketone. It is going to be reduced. One hydrogen added over here and one hydrogen added over here. Here we have a ketone. There is no aldehyde in the molecule, if you see. So one hydrogen added over here, one hydrogen added over here. So in total, there are 6 hydrogens that are added to the molecule. So we can easily write that it's C21. H28 plus 6 gives you 34 and O5. Yes, the R, good. Okay. Next part. Cortisone is an optically active compound. What is meant by optically active? Yes. Can anybody recall what is meant by optically active?
A compound which can rotate.
Which can rotate what?
सर जिसकी फिजिकल और केमिकल प्रॉपर्टी सेम हो मगर प्लेन ऑफ लाइट पे जो है वो उसको लेफ्ट राइट रोटेट कर दे.
Very good. Which can rotate a plane polarized light. To either clockwise or anti-clockwise direction. Instead, you can say that it can rotate the plane polarized light to the opposite directions. Anti-clockwise directions. Okay. We have ended the next question. There are so many questions in this paper. Okay. So it is question number 9. Compare the relative acidities of.
Sir, question 8 है.
Okay, sorry. It's question number 8. Yeah. Compare the relative acidities of ethanol, ethanoic acid, and chloroethanoic acid and phenol. Okay. So chloroethanoic acid is the most acidic one because of a one electron withdrawing group attached to it. Then we have ethanoic acid. Then
Ethanol.
just give me a minute, please. Then we have a ethanol, not ethanol. Then we have a phenol. Phenol is more acidic than ethanol, and the least acidic is ethanol. Okay. So I can write that the strength of acidity depends upon the strength of OH bond, the more the OH bond is weaker, the more it is acidic, because the more it is weaker, the more readily it produces the hydrogen ion. Are these 2 points are clear?
Yes, sir.
Okay. So I can write that chloro ethanoic acid is stronger acid than ethanoic acid because of more electronegative chlorine group. Then I can write that ethanoic acid is more acidic than phenol due to electron withdrawing nature of C double bond O. Then phenol is more acidic than ethanol because of overlapping of p orbital of oxygen with pi system, and the last ethanol is weakest acid among all as alkyl group is electron donating. Is this understandable?
Yes, sir.
Okay. An excess of ethane dioic acid is reacted with warm acidified manganate. State the type of reaction that undergo ethane dioic acid. If you recall, it's an oxidation. What would you observe? Bubbling, because carbon dioxide is formed. Write an equation for this reaction. Use your equation, use atomic oxygen or atomic hydrogen as necessary. So the type of reaction, if you recall, oxidation. Observation would be, there are two observations where you are going to observe the bubbles, and beside this cheminophore is a purple color, so purple to colorless, and bubbles or bubbles, sorry, but this is the significant one because the color change is more obvious. And then you have to write the equation. Okay, so HOOCCOOH with atomic oxygen as its oxidation, and carbon turns into carbon dioxide. We have a 2 carbons over here, so we put 2 over here, and the leftover hydrogens forms water. So if you count, carbon are balanced on both the sides, hydrogen are balanced on both the sides. If you count oxygen, so there are 4 over here and 1 over here, which makes the total oxygen 5. So I would put 5 over here. So now the oxygens are also balanced, and the equation is completed. Is this clear to
सर वहाँ
everyone?
पे 5 क्यों लगेगा? उसके जो COH वाले हैं उसके अंदर भी तो 4 ऑक्सीजन है.
Oh yeah. So no need to put a 5. I overlooked. So there are 4 oxygens over here. So, and there is a 1 oxygen. So yeah, it's balanced. Sorry. Okay. Now, a section of polyester is shown. Draw the structure of the 2 monomers that form this polymer. So if you see, first, if I start from here, I would end over here, because see, these are the 2 complete repeat units, and in these 2 repeat units you are observing the sterling. So it would help me to identify the monomer, that one monomer residue is this and the other monomer residue is this. So this part came from one monomer and this part came from the other monomer. Is this clear to everyone? Now with this O I put an H, and with this C I put an OH. With this O I put an H, and with this C I put an OH. The monomers are completed. Is this clear?
Yes, sir.
This one comes over here, this one goes over here. Okay. Now, serine can polymerize to form 2 different types of condensation polymer, a polyester and a polypeptide. Draw the structure of a polypeptide showing 2 repeat units. If it's a polypeptide, which means there must be a amide links. It's a polyamide as well. The peptide linkage should be shown displayed. Okay. So you have to draw the 2 repeat units. So if you recall, when an amide link is formed, the nitrogen releases one of its hydrogen. So I would make an empty bond. Then here I have a CH, then CH2 two OH. Then from the carboxylic acid, the OH is released. And this carbon is going to bond with the nitrogen of the next monomer. And we would repeat the same structure because there is one monomer only. So it is this way that we do show the two repeat units. This is one repeat unit and this one is the other repeat unit. Is this understandable to everyone? Now, explain why condensation polymers normally biodegradable more readily than the addition polymerization. If we make this one the subject, so I can write that
Condensation polymer can easily hydrolyze.
yeah, because of a ester link or amide link, they can easily hydrolyze. So condensation polymers can easily hydrolyze. Okay. Next question. It's question number 9. Okay. The structure of cyclohexylamine is shown in figure 9.1. Compare the relative basicities of ammonia, cyclohexylamine, and phenylamine. So basically, relative basicity is, if you recall, it depends upon lone pair. So in phenylamine, nitrogen overlaps its lone pair, which is in p orbital with a pi system, making it least stable. And in cyclohexylamine, the hexyl is an alkyl group which donates electrons, so the lone pair is more readily available on nitrogen, making cyclohexylamine most basic. And ammonia having neither an electron donating group or nor electron withdrawing group. So one minute, please. So its basicity is moderate. So relative basicity depends upon the availability of lone pair on nitrogen to accept H positive, the more readily it accepts H positive, the more basic it is. Are these 2 points are understandable to everyone?
Yes, sir.
Okay, so if we look at the formula of cyclohexylamine, it would be C6H11NH2. So C6H11NH2 is most basic as cyclohexyl group is electron donating, and as it is an electron donating, so the availability of lone pair on the nitrogen would be more. It is readily available. In phenylamine C6H5NH2, the lone pair is delocalized, or in the other words, you can say that the p orbital of nitrogen is overlapped. The lone pair is delocalized into pi system. As a result, the lone pair's availability decreases, so it is not able to accept the hydrogen ion more readily. Is this understandable to everyone?
सर क्या हम
Yes.
पाई सिस्टम के बजाय हम ये वर्ड यूज कर सकते हैं बेंजीन रिंग?
Yeah, you can write that benzene ring as well.
थैंक यू सर.
सर ये जो आपने लिखा है relative basicity depends upon the availability, सर ये लिखना जरूरी है, हम डायरेक्ट कंपेयर नहीं कर सकते?
Then you have to see by writing this. I didn't wrote over here that the move. Otherwise, if you don't write that first point, then you have to write that its most basic as cyclohexyl is electron donating. So the lone pair is more readily available on the nitrogen in cyclohexyl to accept the H positive ion. And then after this, I would write that the lone pair is less likely available on the nitrogen to accept the hydrogen ion. So I have to write these points over there then.
ठीक है सर.
Okay, B part. Cyclohexylamine reacts with ethanoyl chloride to form corresponding amide L. Okay. Name the mechanism for this reaction. Yes.
Electrophilic substitution.
It's not electrophilic
सर
substitution.
न्यूक्लियोफाइलिक होगी.
Yeah, it's a nucleophilic substitution, or we can call it addition elimination reaction as well. Okay, we call it addition elimination reaction as well, or nucleophilic substitution as well. Now, that is the same mechanism we did in the last paper.
वो टाइप ऑफ रिएक्शन में आएगा ना, एडिशन एलिमिनेशन मैकेनिज्म.
That is also called, the mechanism is also named as both the way, the nucleophilic substitution or the addition elimination.
Sir, can we write condensation?
Condensation is the name of the reaction, not the mechanism.
Okay, sir.
Complete the mechanism of the reaction between cyclohexylamine and acyl chloride. RNH2 is represent the cyclohexylamine. It's the same, if you recall, we did it in the last class. Include all relevant lone pairs of electrons, curly arrows, charges, and partial charges. Okay, so if you recall, here we have a lone pair. This carbon is partially positive, this oxygen is partially negative. So from this lone pair, the attack on the partial positive charge carbon and this bond broken down hydrolytically. As a result, here I have a single bond with a negative charge. and here this nitrogen is bonded to a hydrogen having a positive charge because it is forming now 4 bonds, and a Cl is bonded over here, then a lone pair, and from this lone pair it again goes here. As a result, the chlorine breaks the bond electrolytically, and the nitrogen breaks the bond with one hydrogen to stabilize itself. And they just written product, so there is no need to write the products over here. Most important, the tail of the curly arrow is either rises from the lone pair or either rises from the middle of the bond, nothing else. That is the most important thing that you have to remember. Now, third part.
Sir, can you repeat?
Yes, I was saying that when we are drawing the curly arrows in the mechanism, the tail of the lone pair either arises from the lone pair or the middle of the bond. There is no third thing from where you can make the tail of the curly arrows.
Right.
There is only these two things, otherwise it is considered to be wrong. Okay, the reaction between cyclohexylamine and an excess of forms compound M. Compound M has the molecular formula C10H17NO to draw the structure of M. I think they have repeated the question from the February-March. These two parts are exactly there in the February-March question. So this is the compound. When cyclohexyl reacts with the acyl chloride, but when there is an more acyl chlorides, excess of acyl chloride, okay, this is cyclohexyl amine, right? What would happen when one acyl chloride comes? The hydrogen from this amine removes, and the Cl from the acyl chloride remove. As a result, the carbon having a C double bond O bonds over here, and the rest of the molecule is there. When there is an excess, so this hydrogen is also going to be substituted, and here we get C double bond O and CH3. Now you can compare the formula of this compound with the given over here. See how many carbons we have? 6 in the ring, 7, 8, 9, 10. How many hydrogens we have? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and one is over here 17. So it's 17, one nitrogen and 2 oxygen. So see, we are getting the same molecular formula as it is. So it is our structure. Is this clear to everyone?
Yes, sir.
Okay, so we have ended, Alhamdulillah, the May-June 2022 paper. My target is that before your exam, we will be able to finish the October-November 2022 and 2023 February-March as well. So, inshallah, our next session will be tomorrow. Okay. So take care, everyone. Allah Hafiz.
Allah Hafiz, sir.
Happy
Allah Hafiz.